Good afternoon, and welcome to the abbreviated online version of the ESIG Tucson Spring Technical Workshop. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As you know, we canceled the physical meeting in Tucson due to the coronavirus situation, and we decided to proceed with a shortened online version. We started the series of 12 webinars in mid-March, and we're running through early May, approximately twice a week. You can find the full schedule at the ESIG website under the Events tab. Recognizing the limitations of a webinar with typically more than 100 people on the line, we'll have individual presentations of 10 or 15 minutes, followed by a few minutes of discussion moderated by the session chair, with hopefully some time for discussion at the end. The lines will be muted, so we ask you to use the question box in the lower right-hand corner of your screen. Today, we'll be hosting Session 8, ESI Planning, Optimization, and Modeling Techniques, chaired by Lindsay Anderson. Lindsay is an associate professor in the College of Engineering at Cornell University and faculty director for energy at Cornell's Atkinson Center for Sustainability. Her current research interests lie broadly in accelerating the transition to a sustainable energy future through integration of renewable resources and leveraging flexibility in DER. Lindsay has been involved with ESIG for several years now, and I consider her a good friend. Lindsay, we appreciate having you here, and I'll now turn it over to you.
Thank you, Charlie, and thank you to everyone who has joined us today for this session. We were really excited about it and glad that we could still hold it even in this new format. Thanks in advance to all the speakers. The only thing I will say is that due to logistical constraints, we've switched the order around just a little bit. So Michael Ferris will be our first presenter of the day. The presentations will be around 10 to 12 minutes, and then we'll have a few minutes to take questions after each speaker. So we'll start with Michael Ferris, who is the Jacques-Louis Lyon Chair and the Stephen C. Kleen Professor of Computer Science, and by courtesy, Mathematics and Industrial and Systems Engineering at the University of Wisconsin-Madison. He's the director of the Data Sciences Hub within the Wisconsin Institutes for Discovery. He received his PhD from the University of Cambridge, England in 1989. And with that, I will turn it over to Professor Ferris to kick off our session.
Hello, everybody. Hope you can hear me. And I'm just going to talk today about short-term economic efficiency and resilience of operations and how I believe that necessitates longer-term planning, policies, and investment strategies. This is joint work with a group of people who call ourselves Werewolf, and that involves Josh Arnold and Adam Christensen from Washington and Wisconsin, and Andy Philpott, who's a colleague of mine from New Zealand. So academics have this wonderful thing that once every 7 years, 6 or 7 years, they can go on sabbatical leave. And so I decided to go on sabbatical leave to New Zealand and was going to do all these fancy things about watching rugby and cricket and going swimming. And then within 20 minutes or 3 days of being there, the newly elected Prime Minister, Jacinda Ardern, came up with a deal. This is a deal between the New Zealand Labour Party and the Green Party. And the deal had, first of all, had the notion of introducing a Zero Carbon Act to establish an independent climate commission. And then that climate commission was going to be requested to plan a transition to 100% renewable electricity by 2035. And as good politicians do, they added some caveat which said that renewable electricity includes for New Zealand geothermal because they have a lot of bubbling things coming up from the volcanic underlyings of their country. And then they also talked about this should be 100% renewable in a normal hydrological year. And so we as mathematicians and engineers were wondering about, well, what do those policy decisions and policy discussions actually mean from an engineering or a practical perspective? The idea was to stimulate some $1 billion of new investment by incorporating that or trying to encourage that with an investment from the government of $100 million. seems like small amounts were in the amounts that we're talking about now with COVID stimulation, but that was what was considered in 2017. So we built a model called Gemstone. So instead of doing all of the fun things on my sabbatical, I built a model instead. And this model was used by the New Zealand Climate Commission, which was created under this to help inform the policy. And I'd just like to tell you briefly three things that come out from that discussion and that use of that model. So the first thing I'd like to say is that policies really do matter. And so if you look at these, all of these figures here, these figures and all of the figures I'll produce in this talk today go on the bottom axis, so go from 0 or business as usual over to very aggressive reductions. And then the policies that are those reductions could actually be a reduction in CO2 emissions. And in these figures here on the left, those are the green bars. Or they could be a different policy which talks about closing down plants. So those are the blue figures or the blue lines which are on these left-hand side graphs here. So as you can see, the green figures our models worked. And the models showed that if we went after the policy of reducing CO2 emissions, then we could do that. And the green figures on the left, I don't know if you can see the pointer, but the green figures on the left actually decrease down towards 0. Whereas in the bottom, the cost increases when you do these things. However, if you change a policy and just say we're going to shut down plants, then if we just talk about shutting down non-renewable plants, then because of the definitions that the economists or the policymakers, the politicians make, then you can see that the net effects on CO2 reductions are less than are idealized in our reductions on the bottom with the CO2 reduction. So that's the first thing. Policies matter. The way you say it, shutting down plants, an action is not the same as a policy which says we want to reduce to 0 CO2 emissions, which is possible within New Zealand because of their large hydro installations. The second thing I'd like to say is that as you go more and more aggressive, so this is the figure on the right of the slide, as you get more and more aggressive, the actual portfolio of the required technologies actually increases. So our model does include a whole swath of different types of technology, both renewable and non-renewable. And as you go from left business as usual to right on these figures, which is going towards 100% renewable, then the swath or the portfolio of technologies that you need increases, and the complexity of how those technologies interact becomes much more complex. Uncertainties and incentives are key to any of these plannings, and that's the third point, is that this model was then enabled the Climate Commission within their November 2019 Climate Act to provide a framework where all of the technologies that we're talking about were present within these kinds of discussions, and actually the benefits and drawbacks of each of the technologies were used. So modeling per se was able to actually affect the discussion at the policy level. But then I came back to Wisconsin, and so as you come back to Wisconsin, models of New Zealand energy system are less relevant, and so we decided to adapt those techniques and generate Werewolf, which is talking about the expansion of renewable energy systems using optimization in Wisconsin. As you can see by this figure, it's clear that my hypothesis here that long-term decisions, so policy decisions or investment decisions, like power plant siting or transmission siting and construction, are on the timescales of 15 years down to maybe 5 years, whereas they are affecting and being driven by decisions that are made at the other right-hand side scale of this graph, which are issues which are operational, either at the 1 day or the 5 minute or even the second or nanosecond operational scale of the electricity grid. And so what Werewolf is aiming to do is actually to try and build tools that are going to enable the people who are making design of infrastructure or policy decisions that are driven by operations and reliability to actually have a model that is actually focused on using the operations to inform the policy decisions and the infrastructure demand. I wanted to be clear that we distinguish between objectives and actions. And so the objectives being things like shutting down power plants, and we're encouraging people to think about policies that are actually objectives and not just actions. And we actually have to worry about a whole bunch of different futures and uncertainties and explore. Our model enables us to explore a much larger design space than normal operational models that actually typically tell you what the investments are at particular stages. Our model enables us to actually do much more than just doing that. Renewable energy makes those uncertainties much more difficult and much more challenging. Not only are the uncertainties those policy or climate style uncertainties that are determined by long scale planning prices or electricity prices or long-term effects, but they're also affected by the operational effects, both of weather and demand, and also the notions, as you're all aware of the duck curve, which shows an increasing need for ramping at different times of the day, and because of renewable electricity, a much higher need for backup capacity to ensure batteries, to ensure supply when we have random renewable generation. In this context, what we build is a model that actually enables that trade-off between those long-term capacity decisions. And in this simplified two-stage stochastic model that I'm having here for all of the nerds amongst you, we talk about capacity decisions, which are decisions or long-term decisions, and I'm thinking of those as variable Z at cost K of Z, and those affect those short-term operating decisions, which are in this simplified model, generation Y, cost C of Y, and the effects of the uncertainties, which might require unload shedding at a cost of Q at a cost of B of Q. What I mean by uncertainties are we have both uncertainties in terms of the types of investment that we can actually do and the development of different technologies and their capabilities. And so different futures correspond to different views of those technologies, but they also encapsulate the different uncertainties which are due to demand or due to prices or even due to intermittent wind and weather effects. And so our model is this two-stage problem, which invests in capacity of type Z, of size Z, and then operates both at Y and Q. So Y is being the operational level of our generators and Q as the load shedding capabilities that we do, in such a way that our demand Y is always less than or equal to the amount that we've installed or our operational level. And Y plus the amount that we load shed has to be bigger than or equal to demand. And like a true mathematician here, I put all of the other operational and physical constraints that I have in my model into Y, Z, YQ being in X. So that encapsulates all of the technical constraints and definitional constraints of the scenarios or the futures that I want to do. The data in this model is very rich. We take data from a whole bunch of different systems, both from the EPA, from NREL, and REITs data, and the annual technology baseline, as well as using data from a whole bunch of census data. And so we build models, and I show you some indication of these models. The data that we generate is at the county scale in Wisconsin, but it can be formulated across any regional area across the United States. And I show the types of data that we have here for offshore wind, onshore wind, and solar generation. Those can actually then be downscaled first to county level, and then the user can customize regions within the model, such as Wisconsin, to generate aggregations of these counties to inform our data with our models with these particular data. We actually have different types of data on transmission, shown in the bottom left here. In the middle, we actually have all of our different scenarios in wind or solar. And then we actually have physical constraints, which are load demand curves, which are also scenario dependent. And I give you some, but also spatially dependent. So we actually have an Illinois-Chicago load demand curve, even though the model Werewolf is being postulated for questions within Wisconsin. So I don't want to go into much details. I probably don't have a lot of time anyway. But we do talk about carbon reductions, and within Wisconsin, we see a very different portfolio of technologies that are relevant for the policymakers. And so the policymakers can see graphs which tell you at each different level of carbon reduction, what would be the portfolio of different techniques or different installations of generation capability. And the graph on the right shows to the people who are making policies the effects or the shutdowns or the reductions in usage of different generation technologies due to the imposition of a policy, which in this case is carbon reduction. It turns out that policymakers like to know, particularly within the legislature, so we've developed this in collaboration with the legislature in Wisconsin, and when the legislature there are interested in regional effects. And so the graphs on the bottom show actually the combustion turbine reductions as we go, or the natural gas reductions as we go towards 100% renewable. And so that's effects are shown there. Similarly, we can see the effects when we go from zero, the business as usual, to 40% carbon reduction. Those are the two figures in the middle of this slide, to an 80% carbon reduction. And as you can see that the wind, which is the bottom three figures, no, the wind is the top three figures, actually increases uniformly over the eastern part of the state, but with somewhat larger wind in Dane County, which is where Madison is, the screaming liberal part of the county. Whereas solar is actually a much more of a hard sell within Wisconsin due to our lovely weather that we're experiencing here right now. I want to challenge everybody or invite everybody here. So I saw there a question. Let me just finish off here, and then I'll come to the question at the end. We presented these models to legislatures and utility owners and the Wisconsin Public Utility Institute, and tried to inform them that our models can help inform policy, and that our models show how effects and the costs of constraints will change policies, or should enable people to talk about different types of policy and how to impose or get to objectives with different techniques or different engineering aspects. Our models couple both reliability in the operational level via a large number of scenarios to the investment decisions that people are making. And the model is currently being refined to enable these people, both in the legislature and in utilities, both public and private within Wisconsin, to actually utilize their data, their private data, in conjunction with our models, so that everybody within the policy debate within Wisconsin is able to use the same model, but inform it with sometimes proprietary data that is only available to certain of the decision makers. We're also extending these models, and the people who know my research, I enjoy solving models which are competitive equilibrium problems. So while we have captured in the talk today the notions of uncertainty and large, long-scale, different time-scale plannings, we also want to, and we have engaged the modelers in modeling problems where each of the agents are acting independently and with different risk profiles. And so the models that I've detailed here, the results are possible to run within a competitive equilibrium framework where everybody is actually acting independently. Each of the utilities are acting independently and acting independently of different sectors of the economic community. And that enables us to look at changes to agricultural policy as well as changes in transportation policy. So that's all I was going to say. I'd love to encourage people who are on the talk here to engage with me, and my email is on the first slide. And I'm quite happy to make this model available. It's actually available. The model is on GitHub, and we're extending it to allow you to use your own data. I have a couple of questions here. Maybe Lindsay is going to shut me up at this stage, but the questions are, does the modeling indicate that increasing renewables, solar and wind, would result in an increase in fast responding regulation requirements? Yes. Or is there a percentage above which regulation requirements could decrease as a result of canceling effects? So there are some canceling effects. People are worried about spinning reserves when we talk to utilities. They're worried about imposing different physical constraints on our model to actually answer questions more definitively of the form that you're talking about. I don't have any slides that actually detail the effects that you're talking about, but there is an increase in fast responding regulation requirements. And we do have mechanisms where we can impose those constraints within our model if the policy wonks understand that these engineering considerations are necessary for their policy increases. The other question I see is, does your future load duration curve factor in efforts to electrify the US, i.e. transportation and heating, etc.? Yes, so there are two ways that we do that. One of which is we could do this exogenously with changes in our load demands, and we have done that both in the New Zealand effects. So New Zealand is electrifying their transportation network, so we added that. But we also do it in a competitive nature. And so a lot of our models in these competitive equilibrium models give rise to a carbon price. And we can use that carbon price to actually model the interactions between different sectors and use that carbon price to value the effects of electrification or changes in agricultural policy, as well as changes in energy policy. And I believe that models of the type, the equilibrium type that we have been building here at Wisconsin will facilitate those discussions to be had more effectively and more informed by science as opposed to good feelings or in political intuition.
So let's, in the interest of staying on time, let's take one more question. Michael, if you want to go ahead and, since you've been reading, we can choose which one, and then hopefully we can address any other ones at the end of the session.
Yeah, so the model does address the flexibility capacity requirement. So we can add flexibility in explicitly as a constraint. And the energy storage capacity requirements are driven to some extent by our scenarios. But if you wanted to have a reserve or some other conditions within this model to answer tau guo, you can actually impose storage capacity requirements as well. Our model does naturally involve investment in battery technologies, even though the battery technologies were used in very limited sense in New Zealand, just because the model also enables you to use stored hydro as an effective battery, and that was important in the New Zealand situation and not so important in the Wisconsin situation. I will address the other questions hopefully at the end of the session.
Great, thanks, Michael. Thanks for the great presentation. Obviously, people were really interested because you had so many questions. Unfortunately, we're going to move on, not unfortunately moving on, but sorry, we ran out of time. Our next speaker is going to be Vijay Vittal, who received the BE degree from the BMS College of Engineering of Bengaluru, India in 1977, the Master of Tech degree from the Indian Institute of Technology, Kanpur, India in 1979, and the PhD degree from Iowa State University in Ames, Iowa in 1982. All of these were in electrical engineering. He's currently a Regents professor at Arizona State University and is the Ira A. Fulton Chair Professor. He's a member of the National Academy of Engineering. And with that, I will turn that over to you, Vijay, for your presentation.
Thank you, Lindsay. Good day, everybody. So this is a project which we recently finished, dealing with electricity and water interdependency, how to model it, how to optimize it, and how to control it. So those were the primary questions we answered. This was funded based on the U.S. National Science Foundation CRISP project, CRISP standing for Critical Resilient Interdependent Infrastructure Systems and Processes. They had a very elaborate multidisciplinary team. Larry Mays is a water systems expert. Junchan Zhang is a middleware expert. Shao Kwan is an analytical psychologist, and she actually did a lot of surveys to build our load models for water supply and electricity supply under situations where we had significant emergencies. And then these were the three students who worked on this particular project. So if you go and analyze what happens with the interdependency between water and electricity, thermoelectric generation and water delivery systems are two critical national infrastructures which are highly interdependent. If one looks into the water delivery system, very, very similar to the electricity delivery system, and they're both highly automated. They have their own SCADAs, which is supervisory control and data acquisition. But these two SCADAs actually don't talk. They operate independently and do not share any information or common observability or controllability. So in this project, we were actually going to build a sophisticated model of the interdependent systems and formulate a tool to simulate the two systems, taking into account this interdependency. And the idea here in the Southwest, the primary interest was to examine the impact of mega droughts and contingencies on these two systems. So we did quite a bit of surveying of water system engineers, electric power system engineers, and talked to a number of experts in this area. So the water delivery system, for people who know about the power system, is very, very, there are several commonalities. There are typically large sources of water. You kind of use a lot of pumps to actually deliver them close to large urban areas. You have some storage in these areas, and then you do treat this water. And then this is, in Arizona, there is the Central Arizona project, which is a large canal system which brings water from the Colorado River towards the primary urban areas of Phoenix and Tucson. And then within the closer to these cities, you have a system which looks very similar to the electricity distribution system, where you have a series of pipes of different diameters, pumps and storage, which basically supply houses with water, or agricultural farms with water in this particular case. And then the major difference between the water delivery system and the electricity delivery system is storage. They have significant amount of storage. They can store water at heads in these water towers which you see, and then they can use them for delivering to the system. So that's one commonality. And then the primary interdependency comes with thermoelectric generation. This is not in the water supply which is there in the boilers. That's a closed system and there is very little top-off required. But the primary use of water is in cooling. And that too, when they do wet cooling using condensers, there's a spray of water on these condenser tubes, and a large part of that water actually evaporates. So that's where the loss occurs. And there are some very fascinating numbers if you see what happens around the country. And I have kind of also shown, so that is one dependency with the power system. And in the water delivery system, starting from the raw source of water all the way up to delivery and treatment, they have a huge number of pumps, stirrers, and various filtration facilities which again require pumping, and they are a huge consumer of electricity. And if you look at the numbers, there's some significant shocking numbers which you will see in the terms of electricity that they use. The other thing which we notice is both power plant operators and water system operators have very good knowledge of the cooling water requirement in terms of electric power system operators or the power plant operators. They know exactly how much water they will use in terms of gallons per minute and for a particular level of generation. And the water system planners and operators basically know what are their pump demands going to be. And so just like in the electricity system, we commit generators and we schedule generators, they actually commit pumps and they schedule pumps. So there's a very, very similar operation taking place. And just like we do day-ahead scheduling, they too do day-ahead scheduling. And it so happens that their scheduling horizon is 1 hour, just like we have the scheduling as a horizon in the power system to be 1 hour. So these are all various commonalities that we see. So here is just an idea of some things around Arizona, just as an example, but I'm sure this is common elsewhere in the country too. So we have this canal system which is operated by opening and closing gates, which are again electrically operated. And then we have large pumping stations, and these pumps are heavy electricity loads. For example, this is a pumping station near Tucson. It has 6 units. It delivers about 621 cubic feet per second, and it has a total pump capability of about 8,100 horsepower. So that is roughly about a 6.4 megawatt load. So it's a fairly significant load, and this is where the primary interdependency with the electric delivery system comes about. So here is the southwestern US, which is very heavily water dependent, and we manage our water really well here. And in this particular case, what we notice is roughly about, on the average in the US, 45% of the water demand is used towards thermoelectric cooling. In some states in the US, for example, Alabama and southeastern, some few southeastern states, it is even higher. So the number I gave you is an average number. So that's kind of a shocking number that 45% of the total water demand in the US goes towards thermoelectric cooling. If you take a state like California, which grows a large amount of fruit and vegetables for the nation, some 15% of the electricity usage in in California, it primarily goes towards pumping needs for irrigation. So that's another shocking number, because that's where you can see the big interdependency coming between these two systems. So in our survey that we saw that electric utilities keep meticulous records of cooling water usage. They know how much water is required for different types of thermal prime mover fuel types. And they have this data for different times of the year, for different times of the day. They calculate this in terms of an average cooling water requirement rate in gallons per megawatt hour. And the key part in all of this is they plan their system so well because of the high dependency on water. Every power plant has two independent cooling water sources, and primarily all of them, by and large in the Southwest, have storage for at least 15 days. So in case of emergency, they can use this storage. So from this, we can immediately recognize that this water usage power output dynamics is a very slow time scale phenomena, and it can basically be approximated by a steady state model. The water system again uses electricity to run pumps, and they too have exhaustive data on the demand for water, the architecture and layout of their water delivery system, and they use this to basically generate optimized pump schedules. They know the rating of these pumps, they know the flow rates and the pump efficiency curves, so they can also calculate the electric power requirements. So the pump schedules can then be optimized to minimize energy consumption. So that is what their scheduling and commitment is based on. So given this understanding that we developed by conducting large surveys, talking to people in both Phoenix and Tempe and other cities, and talking to the water utility and the electricity utilities in the state, we basically came up with the understanding that if you look at this figure, the type of analysis that we would require or the modeling we would require in the time scales of just time series power flow and unit commitment. So this 1 hour schedule really worked for us very well. And since that was the operating horizon for both the water system and the electricity system, we basically did away with the fast dynamics and could capture everything with a series of static power flows on the electricity system. And then we did appropriate optimized unit commitment on the generating units with anticipated operating horizon in the short term. So, and the same thing we basically did an economic dispatch, but in the economic dispatch too, we specifically modeled the pump loads as a separate load by itself because we kept track of it during every hour. And then we also put a cost on water, the operational water cost to account for water usage, very similar to what one would do in an environmental dispatch. And then in the water delivery system, they do very similar things like we do. They model continuity equations at each node, energy equations around pipe loops, and from storage tanks and reservoirs in the network. So they look at pressures at nodes, water quality concentration at nodes, flows in links, and storage tank levels. So for this, they have a very nice piece of software developed by EPA. It is called EPA Net. So we did use this software in our modeling. So this is the basic setup. We basically solve a security constraint unit commitment for the power system. And then we do a combined economic and environmental dispatch. where we include constraints like power flow constraints, generation limits, outputs of units committed and not committed, and pump power demands. We specifically incorporate that into our economic dispatch. And then in the water side, we run their model on this EPA net, and this basically gives an optimal pump schedule over the next hour. So we have done this. We have looked at all the constraints that we use, and then basically we have built up a very nice detailed model, and we have built up an interdependent simulation engine. On the power side, we use a commercial program called PSLF. And then on the water side, we use the EPA net. And, this is like an eye chart, but this just shows what we do. I won't give you all the details. Instead, I'll give you some references which show what we do. This is basically how the system works. We have a inter-networked program control using Python. We do the power system optimization using Ample. We do the simulations on an hourly snapshots using PSLF. And then here we use the EPA net very similarly in the water delivery system. So basically what we have shown is that by doing this interdependent modeling, we can model both electric and water delivery systems. They provide new insights into the impacts and disruptions on the two systems. We have considered several cases of severe droughts. And then we have actually developed a new method by which we can actually show what you have to do to manage this water shortage. Basically, it will put a limit on the maximum generation that you can get out of a thermoelectric plant. And we have developed a very systematic method of actually developing this limit, and we have discussed that in several papers that we have produced. So these are some important references that came out of this work. Since you will have access to these slides, you can see what they are. These are some important papers on the water delivery system modeling. And then we have some papers on modeling the electricity system. And if those who are interested can contact me, and I will show this. So this basically shows the interdependent modeling, this paper in the IEEE Transactions on Energy Management. And this paper on the IET Energy Systems Integration shows you how the interdependent system works. We have a very nice model of the Phoenix area with all the major generation in that area, and you can see how we have gone about doing that. So I'll stop here and open up for questions.
Great, thanks, Vijay. We did have one question that came through privately to the ESIG account. So I'll read that to you. It says, with 1.5 million acre feet per year allotment coming through the CAP from the Colorado, and I believe roughly 1 terawatt hour per year consumption, is there much flexibility in the pumping, or the CAP pumps running near 8760 hours?
There is some flexibility in pumping because the CAP has intermediate storage along the canal system. So depending on, they have to kind of supply some amount of water for irrigation, some amount for the cities, and then SRP is the primary water utility in the state. So SRP manages all the supply from the Central Arizona project, or the Central Arizona project, to the various cities in Arizona. So that's how this takes place. So there is some flexibility. The pumping is not 8760.
Great, thank you. And that is the only question that I saw come through. So with that, thank you very much, Vijay. And we will move on to our next presenter, which is Bethany Frew.
Thank you.
Bethany Frew is a senior engineer in the Strategic Energy Analysis Center at the National Renewable Energy Laboratory. She brings expertise in wholesale markets, as well as developing and using computational models that simulate the planning and operations of the power system. Bethany holds a PhD in Civil and Environmental Engineering from Stanford University. And with that, I will turn that over to Bethany.
Great, thanks, Lindsay. I'm excited to be part of this panel, and I'm going to be focusing on wholesale electricity markets, and specifically the interaction of those markets with operations and investment decisions. A lot of the things I'm going to talk about will build upon things that you've heard previously from Michael, the first presenter. So why do we want to model wholesale electricity markets? There are three reasons that I want to talk through. The first is that wholesale electricity markets exist in many places. Here in the United States, they cover about 2/3 of the load. Second, markets determine the financial incentives that are used to determine operational outcomes as well as investment decisions. And so as we add more low and zero marginal cost resources to the grid, this exacerbates concerns about revenue sufficiency and the linkage that that has with resource adequacy. There's also a lot of uncertainty about what future market design will look like and what market products, for example, will exist. And so as the power system continues to evolve and those market structures evolve, how does that uncertainty stress it stresses this interaction between markets and investment decisions. And so that linkage, markets and investments and the operations that are connected to the market are really the heart of what I'm going to be presenting today. And I think that that captures a key motivation for why we care about wholesale electricity markets is that they do interface with so many other aspects of the power system. The third point is that our current leading computational models don't sufficiently capture this interaction. And so there's room here to improve the modeling capabilities. As one example, our traditional capacity expansion models, which are linear programs, they assume a central planner that's minimizing system cost. And when you run these in a deterministic manner, you inherently guarantee cost recovery. But in the real world, that cost recovery is not guaranteed. There's a lot of inefficiencies or imperfect information, if you will, that results in potentially overbuilding or underbuilding. And so those are some of the dynamics that we want to capture in these interactions. So what are we doing at NREL to address this? We're working on building a new model that captures the impact of market design as well as heterogeneous investors on investment decisions and in turn how that impacts reliability. And when I say reliability here, I'm referring mostly to resource adequacy and load balancing operational timescales. And so this new tool we're calling the Electricity Markets and Investment Suite. I'll mention here a little later that the suite part of this, the S in EMIS, refers to the fact that we have 3 different model formulations that we're developing. And so within this model, we want to represent individual investor firms who have different beliefs about the future and who have different risk representations. We want to be able to explore how different market designs perform under uncertainty and imperfect information. And related to this, we want to show how imperfect information can result in non-optimal investment. So this gets back to the point I made on the previous slide about potential over or underbuilding. And because we have these different firms and in this structure, we want to capture the linkages with operations and markets and investments, this requires a fundamentally different approach, mathematically speaking, and this touches on a lot of the things that the Michael Ferris presented on, and this is a much more difficult approach than what we traditionally do with those linear programming capacity expansion models, and that's what's resulted in the 3 different formulations we have that I'll talk about during the second half of my talk. We're also planning to leverage and integrate with a broader model development activity going on at NREL called SIP, the Scalable Integrated Infrastructure Planning. It's a modeling framework that really reflects our next generation of modeling tools that have greater interoperability, just a more flexible and scalable interface. And I'll talk about that a little later as well. This graphic on the bottom is purely conceptual and illustrative of the types of questions we want to be able to address with this tool. For example, looking at how market designs can evolve over time. For example, maybe moving from today's existing energy revenue dominated with some revenues from capacity and ancillary services to a future where you potentially have a broader suite of market products that explicitly signal and compensate for a wider range of grid services. Not saying that this is what needs to happen, just saying that this is an example of the types of things that we want to be able to evaluate. I want to just take a couple of minutes to talk about the broader landscape, at least from NREL's perspective, and how EMIS fits within that. So first, our existing power system modeling capabilities are shown in this conceptual image with the temporal resolution on the horizontal axis and the spatial or device level resolution on the vertical axis. And you'll see the different color boxes represent different combinations of those spatial and temporal resolutions, which represent different modeling domains. The arrows here are just meant to show how we've established different linkages or soft linkages between these tools as a way to have a more holistic view of the power system. But we put a lot of effort into this, and we have to do it this way because these tools are inherently siloed. They have different modeling, or they're built in different modeling languages. They have different data sets that they're drawing from, and so it's just a lot harder to have that interoperability. And so in part, this has motivated SIP, the Scalable Integrated Infrastructure Planning Framework that I mentioned a couple of slides ago. And the vision is shown here on this slide, where you have the temporal resolution on the x-axis, spatial or device level resolution on the vertical axis, and then you have different panels that go in and out of the screen, which represent different elements of the broader electricity sector. The goal here is to be able to have this framework where you can capture all of these pieces. You're going to have the consistent coding language. Julia is the language in this case. You'll have the same underlying database, and there'll be other just consistent workflows and other factors that you can use to just be able to move between these different pieces more seamlessly, greater interoperability, and in some cases even co-optimization. The panels that are highlighted in white are the ones where we have active development, but again, the vision is someday to be able to represent this full set. I bring this up really because it's important to note that because we plan to integrate within this broader framework, the extent to which SIP has additional capabilities and better representation of all of these features, the more that we're able to access with EMIS to be able to broaden the sets of research questions that we can tackle. Now, just one more kind of conceptual level slide talking about the landscape here is that even within SIP, there's additional effort being placed on improving the economic representation. And so EMIS is one of those, but there are a couple of others I just want to acknowledge briefly, where the horizontal axis here is showing different elements of the broader economy. The vertical axis is showing spatial resolution. And so we have one model called SLIDE being developed that's a general equilibrium model of the fuller economy so that we can capture those broader economy impacts. And then in the bottom left-hand corner, the holistic electricity model is an agent-based approach to look at different regulatory and market structures and how those can allow different social goals to be achieved. And then, of course, EMIS is in the middle. And now I'm going to spend the rest of my time talking about some of the details with that tool. So this is our vision slide. The goal is to represent multiple firms, multiple technologies, different products and timescales, which can be customized by the end user. So I should emphasize here that we're focusing on the model structure, where the end user could then go in, put whatever data set they want inside of it, and they can customize, in this case, the different products. They could customize all of these different pieces to characterize the system that they want to evaluate. We also want to represent multiple project build phases, for example, an interconnection queue phase, and the costs and time lags involved with each of those, as well as economic policy and other scenarios that account for uncertainty. You could have even market design changes themselves, or other cost or price trajectories that you want to play around with. Conceptually, this image here is showing there's two main components to this model. The left-hand side shows the first piece, which is the investment layer, and that's where we have multiple firms who are each trying to maximize their profit. They're maximizing their profit and making investment decisions and doing so based on some expectation of future market clearing outcomes and the revenues that are associated with those. And so the right-hand side is that second layer, which is the market clearing process. And ideally, you would have multiple operational outcomes to represent uncertainty. So you have different scenarios for, again, different economic policy, market design, et cetera. However, as I mentioned before, because this requires a fundamentally different approach than we've historically taken, we have to have three different modeling formulations. The ideal case, which I'll talk about in the next slide, it was not mathematically tractable for us. So I'm going to talk through these three cases now. You can think of them as tracks or as tools. Again, this is the suite, the SUITE part of EMIS for the S. And so what these three tracks represent are various points along a spectrum, or I should say this is one way to think about it, is that they're 3 points along a spectrum, which are shown on the bottom of, or the spectrum shown on the bottom of this slide, where the far left-hand endpoint is perfect competition in an economic sense, which we're calling the idealized competitive equilibrium. That's the first track in this list. The opposite end of the spectrum is what we're calling the exact strategic equilibrium, which is the third point in the third element in our list of three versions, and that is imperfect competition. If you're familiar with complementarity modeling, this is an EPEC, an equilibrium problem with equilibrium constraints. In our case, this was not mathematically tractable, so in its place, we have two different versions that are approximations of this. Oh, sorry, I think I misspoke earlier. The third point in this track is not the exact strategic equilibrium, it's the approximate strategic equilibrium. And then the other element is the agent-based simulation. So again, to summarize, the first item is the perfect competition on the far left. The second and third are the approximation approaches that are sort of to the middle and to the right of this spectrum. So I'm going to talk through each of these individually at a very high level because we don't have time to go into the details. But the first formulation is the idealized competitive equilibrium or the perfect competition. I'm not going to talk through each part on this slide, but the point is that we're modeling this right-hand blue box area where we're maximizing social welfare. We do have multiple investors or firms in this case, but they're homogeneous. And this system is solving for the maximum social welfare given some sort of a set of market supply and demand balance interactions. This is approximately mathematically equivalent to the traditional least cost planning model where you have a central planner who's minimizing the overall system cost. We move to the second formulation, which is what we're calling an agent-based simulation. I'm going to talk through each of these firms separately, but the overall idea is that you have multiple firms who are independently making, and in parallel, making investment decisions without any knowledge of what the other firms are doing. And then they're interacting once those final decisions are made with the actual wholesale market clearing process. So this is somewhat of an iterative kind of stepping forward in time process. So I want to talk through each firm, or just one firm as an example for the process that they go through. And so that's moving from left to right in this upper left blue box. So for this first firm, they have some sort of expectation about what future market prices will be for whatever set of market products the end user has defined. Again, that's a customizable feature. In this case, we're using a simple capacity expansion model. You can think back to the previous slide as a rough example of what that looks like. Based on those price projections, the firms will decide to build and also retire existing units if the NPV, they'll build if the NPV is positive, they'll retire if the NPV is negative. Each firm, again, is doing that separately, and they each have separate beliefs about what the future holds. In our case, as a starting point, we're focusing on different beliefs about what the load growth will be. And so once they make those final decisions for their portfolio, they submit bids to the market for all of the products that exist separately, and then the market clears. And then when those real outcomes are seen by the firms, they can see how well or not how well their beliefs about the future and the resulting investment decisions lined up with their realized market outcomes. So then what we do is we update the beliefs about the future that each of those firms have based on their experience with reality from the previous year, and then we march forward in time to the next solve period until you get to the end of your time horizon. So the idea here is that basically suboptimality, where you can over or underbuild based on some expectation of the future that in many cases is likely not accurate, can be realized. And I also note that we do hope to add additional, we hope to have some sort of Monte Carlo approach where we have different price projections to be able to account for uncertainty in the prices themselves. So the last model formulation, and then I'll wrap up, is what we're calling our approximate strategic equilibrium. So this is using a surrogate modeling approach where we approximate, again, that ideal strategic equilibrium problem. And so the three main steps to this is that we first simulate the market clearing for many different system build-outs. So looking at lots of different portfolios and what the profit outcomes would be associated with each of those. The second step is we use machine learning techniques to derive a set of surrogate functions that link those investment decisions with the resulting profit. And then the third step is that we solve the resulting full problem iteratively, where we optimize each firm's subproblem. In this case, it's the surrogate subproblem separately until they converge onto the final result. So I'm going to stop there. I just want to quickly acknowledge the full set of team members that are involved in this project. They're in the upper left-hand corner of this slide, and thank them for their excellent efforts and contributions. And I'll end there. Thank you.
Thanks so much, Bethany. So going back to the questions, I think the first one, somebody asked if the tool was an open source software.
It will be. So we're in kind of I guess we have another 4 or 5 months left. We'll be releasing that at the end of September of this year. At least the first version. Yeah.
Okay. It looks like there's about 6 questions here, and we're running quite late. So I think what I'll do is maybe just ask one more, and then leave the rest till afterwards, and maybe we can address those later, either in the chat box or at the end of the session. I don't think we'll have time for more, though. Okay. So the next question is, can central operator clears markets, in quotes, allow for layered market clearing, i.e. balancing authority clears wholesale market for bulk power system while the DSO clears market within local distribution area?
Great question. We have not been thinking about the DSO element in here, but as I mentioned, this integration with SIP allows us to tap into other capabilities, and there is a distribution element that is part of that. So future work, I mean, I guess I need to think more about that, but that should not be, I mean, that should be possible, sorry, to be able to account for a DSO or some sort of distribution level. There might need to be some work to maybe define what the rules surrounding that DSO would be, but there's at least a distribution representation that could be part of SIP as a starting point. But I'd need to think more about the specifics of how that would play out.
Great, thanks, Bethany. And you can refer to the chat box for the other questions if you have time. So our next speaker is Sakshi Mishra from the National Renewable Energy Laboratory, where she works on the nexus of renewable energy and artificial intelligence to accelerate the transition toward the smarter and cleaner grid of the future. Sakshi has previously worked as a grid planning engineer at American Electric Power and holds a PE license in the state of California. She has a master's from Carnegie Mellon University in Energy Science, Technology, and Policy, and a bachelor's in Electrical and Electronics Engineering from VIT University in India. And with that, I will let Sakshi take it away.
Thank you, Lindsay. Hello, everyone. Excited to be here presenting one of other NREL's tool, which is a little bit onto the other side, which is behind the meter techno-economic analysis. So I'll be presenting a case study and then show the tool which has been used to conduct the case study. So briefly, agenda is going to be why do we need behind the meter renewable energy optimization, then the case study, then I'll be highlighting the formulation, which is MILP, and a brief overview of REopt toolkit. So why renewable energy optimization? I think the answer is kind of pretty clear that there are various drivers, including falling cost and state RPS requirements and this new area of electrification of the transportation field. So with these drivers, the adoption has been increasing, and worldwide 25% of the power is currently coming from renewable energy, but it is projected that it should reach around 85% to avoid worse impacts of climate change. And among that 85% of renewable energy, so about 31% is projected to be distributed energy resources behind the meter installations of them. And for achieving such transformational level of installations and deployment of DERs, there are complex analysis which need to be done, where we answer questions like, given this utility tariff, this load profile, does it make sense to deploy a PV or a battery system onto my house? And then if we couple the resilience aspect in that analysis, that I want my system to be resilient enough to stay on for 40 hours if an outage were to happen, then how does the technical as well as economic factors play out within that complex analysis? So that's the question we set out to answer using REopt Lite tool. And this is a case study which is demonstrating one such example. So this case study is answering the question, determining the optimal DER size with the capability to sustain a predefined outage. So here we choose a mass manufacturing plant in Denver area with a given yearly energy consumption. And then it has existing PV system onto it, which is about 500 kilowatts, and we want to assess DER options, which is additional PV as well as battery. The analysis focus is resilience, and we are predefining the outage as 48-hour long outage, but still the objective of analysis is cost minimization, keeping the resilience constraint as priority. And the critical load is defined as 65% of the total load, which needs to be on once the grid outage happens. So this is how the load profile looks like for the manufacturing plant. It's weekday and weekend almost the same, and peaking around 4 a.m. when the machines power up and they draw the maximum amount of current for motors to start, and pretty much same throughout the week as well as months. The utility tariff which was used was from Public Service Company of Colorado, and it's called Secondary Photovoltaic Time of the Use Schedule tariff, and it has energy as well as demand charges, and the rates as well as the adjustments get added as the actual rate which is being considered. There is a link to the page where this utility data, tariff data comes from. So after running the optimization using MILP, these are the results which REopt recommends, where recommended size of PV is around 3,000 kilowatt, and then a big chunk of battery as well. So as you can see towards the black box, towards the end of the slide, the black box says it's a negative net present value. So it is essentially a cost which needs to be paid over the life cycle of the project. And this is happening because we have imposed the resilience constraint that our system needs to be independently able to meet 65% of the load. And for that, designing the PV and battery sizes such that it does. So that's why we see a negative cost here. But one thing to note here is that this method does not incorporate value of lost load. And if we were to incorporate that value, this number will surely go down and may become positive depending on the case. So this table shows the results from resilience versus financial focus. So as I was explaining earlier, that when it is resilience focused, though the objective is still cost minimization, but the constraint of the resilience that the system should be resilient enough to meet 48 hours of outage gets superimposed, and that causes the system sizing of PV battery to go high versus the right side column, where in financial, if it were to be a purely financial analysis, meaning still considering the technical components and aspects, but not imposing resilience or constraints, then it doesn't make sense to install PV and battery for the site. This plot shows the system performance over 1 year, and the light blue box shows the outage duration when PV is serving the load as well as it is charging the battery, which gets discharged and again charged by PV. So the combination of PV and battery therefore is able to meet 48 hours of outage duration and 65% of the load, which is the critical load percentage specified. The next slide here is showing the outage simulation. So the architecture of REopt Lite tool is such that the first module is about optimization, where a predefined outage is given as input to design the system. And once the system is designed and PV and battery size has been recommended, the second module does the outage simulation. So it's a simulation-based module which runs on load following rule-based strategy to understand that if the outage were not to be the fixed one which was specified into the as input, and if we ran this, if we randomly simulated outages throughout the year, starting first hour, second hour, third hour, and then not fixing the length of the outage, instead looking at if the outage were to start 18th hour of the year, given 87, 60 hours, then how long will the system which was recommended by the optimization module, how long will it be able to sustain the outage? So in this plot, on the left side, it's for the, and the tab we are looking at is the monthly tab where the results are aggregated over the month to find the probability of system survival if the outage were to start in the month of January, for example. The leftmost column is for resilience case, where we can see that in the month of January, the duration of outage is 50 hours, 0 probability, versus the month of September, as an example. The system designed with resilience constraint, resilience focus is able to actually go on for about 100 hours. That's when the probability drops to 0%. So it's important to understand why such a variation. It's essentially because the load profile varies as well as PV resource profile varies. So maybe in the month of September, this is how it works out, that PV is able to meet the load and charge the battery enough so that when PV goes down, battery can keep sustaining the 65% of the load till PV comes back next day. So that's how the duration of outage survival stretches out to 100 hours at times for a certain month. A quick highlight onto the optimization formulation which is used for this for REopt Lite, which is MILP, with the optimization of life cycle cost minimization. It uses 1 year of resource and cost data with present worth factors to account for the lifetime costs, which can be 20 or 25-year analysis period. And then it assumes that the first year repeats with degradation and escalation factors incorporated. It can do hourly as well as sub-hourly analysis. The example which we saw was for the hourly analysis, and it makes sure the load is met from some combination of either grid purchases or on-site generation or discharge from the battery storage. And when there is an outage, only on-site assets can meet the load. But at this point, it does not consider power flow or transient effects. So it's essentially a behind-the-meter energy optimization model. And technology modules which are modeled within are based on empirical operating data. And it finds optimal technology sizes, which can be 0. That's where the mixed integer linear programming, so integer parts come in 0 or 1 design choice of whether to use this technology or not. And then it does so with the constraints which are subject to resource, operating in market aspects. As a quick overview, it takes in renewable energy generation, conventional generation energy storage as inputs, and combined heat and power model is under development right now. And then the drivers are cost minimization, economics of capital cost of the technology, various incentives, and financial parameters. And it also accounts for utility costs, which have their various components, energy demand, installation rate. With these drivers, it gives the output recommendation of whether to install a technology or not. If yes, then how much to install. It also gives the first year optimal dispatch, showing how should the battery be dispatched for operational cost minimization, where it does peak shaving or energy arbitrage, both of them at the same time. Ways to work with REopt: there is a comprehensive internal model which has been around for more than a decade, and REopt Lite version is a web tool which has been out for a couple of years now. Since 2017, it's a web tool, as well as it's available as an API, which allows for the programmatic access, which helps with sensitivity analysis of more number of scenarios need to be run at the same time. The API comes in pretty handy. And REopt source code has been made open source just recently, a couple of months ago. So please do check it out if you're interested. And in summary, it's an optimization model which is facilitating answers to complex questions about behind the meter system design and dispatch, considering resilience as well. And results are driven by economic objective, which is cost minimization. And one thing to note that is the size, technology mix, and dispatch is not a user input. So users can constrain that we only want maximum PV to be assessed as 500 kilowatt from 0 to 500, but model does this decision and recommends the size of the PV which should be installed for minimization cost objective. And so that way users can force technology type and sizing by setting the constraints, input to the constraints accordingly. So that will be all, and these are some resources to look into if you're interested. Thank you, Lindsay.
Great, thanks very much. So I'll go right into the questions. The first question is, what are the different ways to calculate the resilience value for a commercial customer? Does the value of lost load use SAIDI/SAIFI, or are there other metrics that are more suitable?
So currently, how resilience is evaluated is really we give the input in terms of number of hours which we want system to sustain without utility being present, as well as the amount of critical load, which can be 50%, 30%, depending on the customer side. And then REopt does the analysis, but it is not currently considering the value of lost load, for example. So that's something which can be a post-processing module, which can be added on the top of REopt analysis to understand on case-by-case basis.
Great. Okay. And then the next question is, and then we'll have to leave the rest till later, we're already running a little bit late. But second question will be, this could be a bit off topic, but since you're working on applications of machine learning and power systems, how do you think using machine learning justifies over using any mathematical approaches, providing similar accuracy in the real time?
So it depends. It's very much dependent on application. There are certain applications where optimization and traditional methods make much more sense than machine learning, but there are places where using machine learning has shown better accuracies. And one of the examples, for example, is a forecasting domain where I have recently worked on a project which is not REopt, but where we are predicting solar resource, for example, and we have seen accuracy gains above 50% based on the traditional statistics-based methodology. So that's where it shines. And at the same time, actually, it does not have to be two different opposite directions to pursue. It is possible to do modeling where we are using machine learning and also incorporating physics-based knowledge within the framework. So in such a way that machine learning is augmenting the classical analysis, which leverages both classical as well as machine learning. Yeah.
Great, thank you. Okay, so our next speaker and our final speaker is Roald. She's an assistant professor and Granger Institute Fellow in the Department of Electrical and Computer Engineering at the University of Wisconsin-Madison. She received her PhD in electrical engineering in 2016 from ETH Zurich, Switzerland, and was a postdoctoral research fellow with the Center of Nonlinear Studies at Los Alamos National Laboratory. Her research interests focus on modeling and optimization of energy systems with a particular focus on managing uncertainty and risk from renewable energy variability and component failures. Okay, take it away, Lena.
Oh, okay. Thank you, Lindsay. So I hope you can hear me all. Yeah. Okay. So I'm gonna. I mean, I know that we're getting to the tail end of this session, and there's about, I guess, like 12 minutes left on the original agenda. So I'll try and give you some quick kind of takeaways here at the end. So the topic of my presentation here today is on gas electricity system constraints. And so before I sort of head into this, I just want to acknowledge the people I've been working on this topic with. And both at Los Alamos National Lab and also at ETH in Zurich. And I want to highlight just Anatoly Slotnik, who's currently a staff member at Los Alamos, and Connor O'Malley, who's a PhD student at ETH Zurich. And this has been fantastically fun work, and I want to acknowledge their contributions. Okay, so essentially, the topic and sort of the motivation for our work here is increasing gas electricity interdependency. And essentially, kind of the key component here, which I'm sure most of the people who are here are very well aware of, is that gas-fired power generation is expanding and has been expanding for about the last 10, 15 years. So we've seen a huge increase in the amount of electricity generation that comes from natural gas power plants. And currently in the US, about 40% of the total energy mix is electricity coming from natural gas. And of course, as a power system person, I mean, I'm very happy that there is natural gas because natural gas is so flexible and really enables us to integrate renewable energy better and also enables sort of this fast up and down ramping that is often needed in order to take care of load peaks. So you can see that in the little one of the figures that I put up here. The upper one is a figure from the national grid in the UK, where the orange part, which is the spiky part that kind of increases and decreases day by day, that is the generation that comes from combined cycle gas turbines. I just think this picture is a really good example of how important natural gas is currently in order to ensure that we have sufficient flexibility to serve load with variable renewables and all sorts of up and downs of demand that we see in the system. However, although we are really fond of this sort of flexibility from natural gas as power systems people, the impact that this flexibility and this kind of ramping up and down by natural gas power plant has on the natural gas system can be quite challenging. So specifically with these huge increase in gas loads from natural gas power plants, gas pipeline loads have been changing a lot. I think that on the figure on the bottom right here, you can see this is the scheduled versus the physical flow on the El Paso pipeline. And you can see that this like thin blue line here, which is the scheduled flow, it's kind of, I mean, it's going up and down, but it's rather constant. But then when you look at the physical flow, you just see how much it's going up and down. And with these changes in the flow and changes in the offtakes of gas, we also get changes in the pressures. And in the natural gas system, if you do get too low pressures, you end up in a situation where you have a possibility of getting an explosion. Or if you have too high pressure, you can also get explosions. And so it's just like really, really dangerous. You have to be very careful how you operate this natural gas system. So sort of just acknowledging that, our viewpoint here is sort of how can we make sure that the system, the electric system operators are able to take gas from the electric system, from the natural gas system. They are able to take use the gas in a way that does not jeopardize the security of the gas system. Because if the security of the gas system gets jeopardized, the reality is that the first customers to be curtailed are natural gas power plants. And if the natural gas power plant uses its fuel, then that can have big impacts on electric system reliability. So currently there are several barriers to making sure that we are able to maintain this reliable supply of gas. So first of all, there's a lack of coordination between electric system operators and natural gas system operators and pipeline operators. So there's a need for increased information sharing, which can be really challenging because there are also barriers, regulatory barriers to sharing too much information. There's also questions of markets and how markets are not timed and coordinated in appropriate ways. And so there's definitely a question of coordination. There's also a question of operational practices. So the natural gas system and the pipelines, they also rely on compressors to pump gas through the system. And the way these compressors are operated as of today, it's kind of similar. I mean, as Vijay was mentioning about the water system, people are dispatching pumps in order to pump water. The gas pipeline operators are also dispatching compressors in order to push gas through the system. But we are seeing that there might be maybe different ways in which we can utilize those compressors that are out there better in order to make sure that the gas is available at the point in time and in space where it is needed, so that we are able to actually withdraw the gas we need for electric system generation. just I wanted just to highlight here a couple of differences between gas and electric systems that kind of make it challenging to coordinate them. And one of them, and kind of one of the key components here, is that the gas system actually has like kind of inherent storage in it. So essentially, gas system stores a lot of natural gas in the pipes. So in order to maintain that high pressure, there has to be a lot of gas inside the pipe. And if you have a gas pressure that is higher than what you would necessarily have to have to be secure, you have some extra slack. You can withdraw a little bit more gas for a while than what you're putting into the system in order to, and you will still be able to maintain safe system operations. So that means that in power grids, we kind of have this balancing that is happening at the second-to-second scale, right? And there are very fast dynamics. Whereas in the gas pipelines, we only need like daily or monthly balancing. Whereas in power grids, storage is costly. Gas pipelines kind of have this inherent storage. And there's also this thing I mentioned about electric reliability being sort of that is there for all customers. But in the gas system, the contracting that happens with the natural gas power plants is such that they are typically the first customers to be curtailed. There's also differences in how the markets are structured and the timing of the markets. And then one important thing that is related to this question of balancing and storage is that the power grid reaches steady state in seconds, whereas a gas pipeline typically takes hours to reach steady state. And we could kind of argue that in an operational time frame, the gas pipeline essentially never reaches steady state. So these are some of the challenges that are there in then trying to make sure that these systems are interacting well with each other, is that you have to take into account that the gas system has a very, very slow dynamics. And the first thing I wanted to show you here today is just sort of like how important is it that we're actually taking this sort of like dynamic modeling into account when we are doing modeling of the gas system. So how important is it that we're looking at the dynamic model instead of a steady state model? And so essentially, I'm not going to go into detail about these models, but the steady state gas system is essentially kind of, you just let the system run at its current point, like sort of input and outputs, and then you kind of see where it settles down to. Whereas in the dynamic gas modeling, you are continuously accounting for how changes in the operational set points are going to change the operational conditions. And so here is just a very tiny example. This is like a 3-pipe system. We have a slack node at the top where the gas is coming in, and it's being withdrawn down there at node number 4 and number 3. And essentially in this little simulation that I'm going to show you, we are starting from a steady state point, and then we're swapping the loads. And so essentially, you can see here what I've drawn is the steady state solution and the dynamic solution. So the dynamics is there in blue, and the steady state is in black, dashed line. And this is showing the slack pressure at the, this is showing the pressure at node 3 as a percentage of the slack pressure over 10 hours. And you see that after about 1 hour, we are swapping these loads. And you can see that the steady state immediately bounces to this higher pressure, whereas the dynamic modeling takes much longer to reach there. And the dynamic is kind of the true this is the true representation of what's going on in the system. So the system takes much, much longer than what the steady state is assuming for it to reach that new point. And in particular, and this takes really long, it takes more than 5 hours, and probably before those 5 hours are gone, we would already have switched to a new operating point. So then I just wanted to say here that kind of the takeaway that I also want you to take from this is that it takes a very long time for the gas system to reach a new steady state operating point. And also, and it's essentially never in steady state. And if we choose to use just a steady state solution as an approximation of what the gas system is doing, we actually end up with solutions that can be really dangerous. So there might be pressure drops that we're not seeing. There might be pressure drops that are larger than what we would expect. And all of this can lead to problems. So just kind of rushing quickly into the last part here, what I mentioned in the beginning that we also have these questions of sort of how can we coordinate the power grids and the gas pipelines better? And what is the value of doing that coordination versus maybe just investing in better opportunities to control the gas pipelines better? So this is, I'm just going to very quickly go through this. There are 4 operational scenarios here. So the first scenario is essentially the operation today. And you can see here in the graphic on the right that we are sort of looking at the x-axis. We have like gas operation that is kind of more constant and more dynamic. So this is the dynamic one, kind of represents the better kind of control. And on the x-axis, on the y-axis, we have the coordination. So essentially, as we're moving from like sort of the corner here, like the scenario 1, which is sort of operation today, towards the scenario 4, where we have both better gas operation and better coordination, we are sort of investing both more in information exchange between those entities, and also we expect our problems to become computationally more challenging. Okay, so I'm just going to take you through those scenarios. And essentially what is happening here, I mean, is that we're solving this big optimization problem where we're solving essentially a DC optimal power flow, a dynamic optimal gas flow, and then we have the coupling constraints that represent how the gas power plants are withdrawing power from the gas system. If I look at this, this is just a small test case here just to illustrate what can happen. And so for today's scenario, really what's going on is that the generation dispatch from the OPS is kind of passed on in some form to the gas system operator. The gas system operator is assuming that the gas is kind of withdrawn at a constant rate, more or less, and might want to just run their compressors at the constant compression rate throughout the day. Just, I mean, because that's maybe, you know, the things that they tend to do. And that unfortunately then leads to pressure violations. And then we also, we see that if we want to invest in somewhat better control capabilities, what is happening is that we take the same dispatch from the optimal power flow from the electric system, but now we are allowing the gas system operators to actually, operate their compressors in a better way. And actually, we see that it's possible for them in this case to then make sure that the pressure stays within its bounds. We also have a third scenario here, which is sort of like we maintain the same kind of control. So you see the compression ratios here, which is the second part of the plot here. They remain still constant in this case. But in this case, we are assuming that the gas and electricity system operators are talking to each other, and they are making sure that they are able to come up with a solution that respects the pressure bounds. And so essentially here we just see that, you know, pressure is okay, but we get a higher cost in this case. And then in our kind of dream scenario, we actually see that, you know, we can both operate the compressors in the way we in this dynamic fashion, and then we actually see that it is possible for us to facilitate the solution that comes out of the optimal power flow. So in this case that we're looking at here, the scenarios 2 and scenarios 4 are actually the same. So in this case, it really was worthwhile to invest in better control and better coordination, what's not really important. But the question is that if we go to a higher loading scenario, then these things change. So what we see here is that if in the setting where we don't have any coordination, the problem actually becomes infeasible. Whereas if we do have some coordination, then we are able to get so much lower costs if we are investing in both having better coordination and having better control. Okay, so I know that this is going pretty fast here, but I just wanted to try and get to the end. So essentially, the summary and the things that I would like you to take away here is that it's really important to account for gas system dynamics when you're analyzing gas system operations, because it can otherwise lead to dangerous solutions. The operation of gas electric infrastructures can be improved through better control and better coordination. And which of those two are the best ones to invest in kind of depends on the loading scenario. If you have a low to medium load case, maybe better control is sufficient. That was what we saw in our test case. But if you have a high loading case, you might need to have both improved coordination and also better control. All right, so I'll stop there. Let's see if we have time at all for any.
Great. Thank you for giving us your fast version. You did great. So there's a couple of questions here. So the first one is, due to the lead time required for the natural gas pipeline system to reach steady state, how do you foresee the complexity of natural gas pipelines plus storage adapting as turbines in the future are retrofit for hydrogen or alternative operations?
Oh, that's an interesting question. So I don't. So I'm not sure exactly. So particularly the setting that we are interested in here has been the operational time frame. And at the operational time frame, I am not sure entirely how, for example, using hydrogen as an alternative fuel would work out. And one thing that is sort of happening is that because of this fuel uncertainty for natural gas turbines, I mean, there has been investments into dual fuel capabilities. And so maybe we would see something, maybe that would be kind of also, I mean, that would maybe give rise to similar complexity. But I will admit, I mean, this is not a question that I have thought about in detail, but it's definitely a very interesting one.
Great. And the last question of the day is to both Vijay and Lena. And it says, is there an opportunity to also study the existing communications infrastructure to derive maximum value for our investments in power, gas, and water systems?
So I didn't show some of that, but we have actually done that. We have used this middleware to actually connect the two SCADAs in our emulation of the water and electricity systems. And we do send price signals and other usage signals to each of the other SCADAs. And we have kind of simulated a scenario where we show an extreme drought and have kind of developed a very systematic method to limit thermoelectric generation output based on water availability and the storage on site. And it kind of really show, and then when the drought goes away, we show how automatically the limit on the plant increases. And so that is all done through this emulation where the information is passed between the SCADA from one system to the other.
Yeah, I think that's also, yeah, no, that sounds very interesting. I could also just see that with gas and electricity, I know that there are also regulatory barriers to have certain kinds of information exchange, because it then relates to kind of, there's kind of a competition between like gas systems and electric systems in certain areas. So at least in many places, that can be kind of regulatory barriers to exchanging the information could potentially be as challenging maybe to deal with as the technical ones. But yeah, I mean, ideally, of course, it would be great to have some automatic exchange there.
Great. Okay, so there have been a couple more questions come in since I said that was the last question. So if you don't mind, we'll take one more and then we can wrap up a little bit late, maybe 10 minutes. Okay, so the next question is, in the gas system, how common is it for a natural gas plant to have its gas curtailed, and how often do low pressure violations occur?
Yes, so this is a good question. I mean, the kind of the typical case and what like really led to very big concerns about this is the case of sort of particularly in New England, when you have very cold weather, like a polar vortex situation. And then you can have, because of the contract structure of the gas power plants and how they procure their gas, there are different ways of procuring gas. Gas can be procured in long-term contracts, but they are more expensive. So you have to send, you kind of pay for capacity in the gas system over the longer term. But then for most gas power plants, they will rather buy capacity in a shorter term time frame because that's typically more economical. But then these contracts are also the ones that then suffer when there is a very high demand for gas. So it's a little bit also kind of, I think that I mean, over the last few years, there's also been work, and I think also my impression is that the system operators are getting better at communicating with the gas power plants also about their fuel availability. I know that ISO New England is also working at doing forecasts of fuel availability for natural gas power plants, so like more on a week ahead basis during cold weather periods. And so it's I cannot give you like exact numbers, but I would say it is common enough that this is a concern to the electric system operators that they might lose potentially many gas power plants at the same time. So.
Okay, great, thank you. So I guess we are 10 minutes over, so it's about time to wrap it up. So I want to take this opportunity to thank all the panelists for their presentations today and to thank all of you in the audience for your participation and your great questions. In this session, we've had a great overview of some cutting-edge optimization problems for integrated energy systems and markets that are relevant to complex problems facing utilities today. And in fact, Charlie's already suggested a future follow-on session with industry panelists to explore the continued translation to wider industrial applications. So while you wait for that, I'd like to remind you all that the next Tucson webinar, session 9 on operations planning for storage and hybrid power plants will be held on Thursday, April 23rd at 12 noon Eastern. You can find the full schedule of upcoming sessions on the ESIG website. Thanks again for your participation. Stay safe, and we look forward to seeing you the next time around.